So today we're going to be talking about Gibbs phase rule and how we can calculate the degrees of freedom in certain systems. So first, we want to talk about Gibbs phase rule. Now, when we talk about Gibbs phase rule, we want to talk about a couple things, right? So if we assume, let's say, some system here, it's some three-level system. Let's say we have a vapor phase here. We have some alpha liquid phase, some beta liquid phase here. So we have in things like this, in certain systems like this, we can have some p amount of phases. So we could say for this one that p is equal to 3. We have 3 phases here to talk about. And so what we can talk about now is something we want to call the chemical potential. And the chemical potential is simply defined as the derivative of the total Gibbs free energy, which is the number of moles times the Gibbs energy per mole, with respect to the change in moles when we keep the temperature, pressure, and some moles J not equal to I. And we talk about that because we're talking about some change in mole when we're looking at these separate mole fractions. So that's the other thing we talk about, the fact that we have components here that are part of mole fractions. So let me get this out of the way really quickly. Just know that that's the definition for our chemical potential. Now, for each one of these levels here, we're going to have some components for it. So we say that this is some components. We have a like y1, that's a component. There's going to be y2 component, a y3 component, and yada yada yada, all the way up to a yc component, some c amount of components. And it's the same thing for the liquid phase. You're going to have a y alpha 1, y alpha 2, y alpha 3, yada yada yada. Going to have some c amounts of alpha components, and then we're going to have some c amount of beta components too. And so when we look at things like this, we're gonna have some c amount of components for each one of these. And so we get into talking about something we call the intensive variables. Intensive variables. And these are variables that don't depend on the size of, I guess, the system. So now we talk about what intensive variables do we have? Well, for one, we have the mole fractions, and the mole fractions don't depend on the number of phases there are, right? So we could start off by just labeling our p, our number of phases, and then we look at the number of components. So label that as just C, the C amount of components. And so how many of these do we really need? Well, we look at the fact that we have C components. So really, we just need C minus 1 components because we could find the sum of this component by doing 1 minus the sum of the remainders here. So C minus 1 is the number of mole fractions. And then we also need to add 2 because remember, we have temperature and pressure. So this first equation is representative of the number of unknowns, the number of intensive variables we have within this multi-phase system. Well, now that we have our intensive variables, we can also deal with how many equations we have, right? And we specifically want to look at the equilibria equations. And so, there we go. How many equations do we really have? Well, we can go back to talking about our chemical potential. And so when we look back up here, we see that when we have a multi-phase system in equilibrium, we're going to have, start off with here, we're going to have the chemical potential of the vapor phase is going to equal the chemical potential of the alpha liquid phase. So that's one equation, and we're going to have C of these, because remember, if we have C components, we're going to have C equations. And so we can write down the same thing for the chemical potential of the alpha liquid phase is equal to the chemical potential of the beta liquid phase. And again, we're going to have C of these, C components, C equations. Now, when we look at this, we could also say, oh, so wouldn't the vapor phase also have to equal the beta phase? So we have to write down a whole new equation for that. And to that we say, well, no, because that's implied. We already have these two equivalences. So just to say that the chemical potential of the vapor phase is equal to the chemical potential of the liquid beta phase, it's just redundant. It's not necessary for us to rewrite that. And so how we can rewrite this is, so since we have C of these components, going to start that off, and we're going to multiply this by the number of phases minus 1, because at some point you're going to have some equivalence between two of these, which will take out one of the equations just for the sake of not being redundant in our equation. And so there's a specific term for this, and that specific term is called the equivalences of chemical potential. Chemical potential. And it's called that because, quite literally, we are just equating the chemical potentials of a phase system that's in equilibrium. So that's how we get to know the equilibrium equations here. Now, the last step in deriving Gibbs phase rule is combining these two equations. So we have P times C minus 1 plus 2. And we're going to subtract our other equation, which is C times P minus 1. And the reason we're subtracting this is to get rid of any similarities in between and just get the amount of actual unknown variables that we are going to have to take a look at, the number of degrees of freedom when we look at these sorts of equations, or these sorts of systems. So we can distribute out the P. So this is PC minus P plus 2. And we're going to subtract PC minus C. And so these two PCs will cancel out. We're going to be subtracting a negative, which will make it a positive. So this is how we get to our final C minus P plus 2. And that is Gibbs phase rule. Gibbs phase rule, which calculates the degrees of freedom in a multi-phase system, much like the one that we were working with before. Now, what we can do with Gibbs phase rule is we can start applying it to certain systems, right? So let's say we have some pure water, right? And we want to go at the triple point. And the triple point, triple point. So at the triple point, of course, we're going to have 3 phases, and we have one component, which is just pure water. So if we apply Gibbs phase rule, we have one component minus 3 phases plus 2. So 1 minus 3 is negative 2 plus 2, and that's just equal to 0. So we have 0 degrees of freedom. Why is it doing that? Degrees of freedom. And that kind of makes sense because the triple point is not something that we can necessarily define. It's something defined by nature itself. So we can't change anything about it. It is 1 point on that pressure temperature graph, if you remember that. And it makes a bit more sense when we talk about, let's say instead of H2O at the triple point, we're going to go H2O where only liquid and vapor exists. So we have, again, one component. We have two phases, 1 minus 2 plus 2. And so that's just going to be 1 degree of freedom. And that does make sense because if we look at, let's say this is our pressure temperature graph. That's going to look something like this, right? Here's our triple point. At our triple point, we only have one combination of pressure and temperatures to get to that triple point. It is a set defined point on this pressure temperature graph. This is for water. Now, if we are looking between our liquid and vapor phases, there is a whole lot more we can change. We could say, oh, I want to go at this pressure. Well, this pressure is going to lead you to this temperature. Say, I want to be at this temperature. Well, this temperature is going to lead you to this pressure. So there is 1 degree of freedom we can adjust to get either a different pressure output or a different temperature output. So this is how we can apply it to these sorts of systems. Now, another type of system we could do is instead of just having a pure component of just one thing, we could have a mixture of things. So let's say we have a mixture of water and ethanol. And ethanol is CH3CH2OH. So we have two components now. And let's say that they coexist in the vapor and liquid phases, right? So now we have two phases. We have two components. We have two phases. And so we're going to go 2 minus 2 plus 2. And of course, that's 2. So now we look at a system where we have 2 degrees of freedom. And so you might be wondering, it's like, wait, how does that work? So let's draw this out maybe. We have our vapor phase, we have our liquid phase. And so when we say that we have 2 degrees of freedom, there's a couple things that we can adjust. The first one that might jump out to your mind is like, oh, that means we can set both the temperature and the pressure of the system, right? So we could say, oh, the temperature is going to equal this many things. The pressure is going to equal this many. And so what are we setting after that? Well, to look at that, let's say we set the temperature at some value. What else is in play here? Well, we talked earlier that we have a mole fraction. There's a mole fraction of component 1 and component 2, mole fraction of, y1, y2. There's our mole fraction. So at the point where we set one of these mole fractions equal to something, the system is determined. We cannot change any more things. We cannot specify any more things because at this point, everything else is set in stone. We have used up all our degrees of freedom. So that's how we can use Gibbs phase rule to find the degrees of freedom in certain multi-phase systems with multiple components and multiple phases. And that rounds out this homework.